So the next speaker is Dani Futer from Temple, generic quotients of cubulated hyperbolic groups.
Well, thank you to the organizers for inviting me. This is a lovely conference, and it's a privilege to be a part of it. Everything I say is going to be joint work with Dani Wise. Also, apologies to the third of the audience that started this talk in Israel a month ago. Hopefully this will be something new for the remaining two-thirds. So I do want to start with definitions, so I should tell you what cubulated hyperbolic groups are. You heard about it at Jason's talk this morning. It'll be almost exactly the same in mine. Hyperbolic groups. So, definition, G is cubulated. Following Jason's lead, I'm going to put a star for the ever so slightly non-standard definition. If G is the fundamental group of X, where X is a compact, non-positively curved cube complex. So the non-standard part of the definition for this talk is that I want my groups to be torsion-free. I want them to be fundamental groups of cube complexes and therefore acting freely on the universal cover. Cover X tilde is going to be a cat-zero cube complex. And G is hyperbolic if G is a fundamental group of some space, not necessarily a cube complex, where the universal cover is, well, tilde or something. Okay. And as we also heard in Jason's talk, when you put those two hypotheses together, cubulated and hyperbolic, you get some extremely nice consequences. So let me list a couple by way of a survey. So cubulated plus hyperbolic is a powerful combination whereby the theorem of Hegel, this implies that G, in fact, the cube complex itself, is virtually special. So it virtually embeds into a right-angled Artin group by an earlier theorem of Haglund and Wise. This is implications of now virtual specialness. Quasi-convex subgroups are separable. So we can take immersions into this cube complex and look into embeddings in finite covers by the theorem of Davis and Cavage. C dead. G is linear. G is also large. I forget the attribution for this. Is it Antolin Manassian, maybe? Somebody in the audience wrote a book about properties of three manifold groups, where this is very nicely spelled out. I forget the attribution, but you do get that finite index subgroups surject the free groups, so you get lots and lots and lots of nice properties of the group. That's one reason why having the two together is a very nice combination, and the point of this talk is to what extent this is going to hold in quotients, particularly generic quotients. Questions so far? Okay. So part two, we're going to talk about quotients. So we're going to start with group of this type. So let's say X a non-positively curved cube complex. We'll start with a cubical group. We're going to choose a bunch of geodesics and cone them off. So a cubical presentation is X star So this is something in the form X, where I've chosen a bunch of geodesics, GK, where the GI are closed local geodesics. So I've taken some loops and made them as tight as possible. And then we're going to think of these geodesics as conjugacy classes or relators.
In the one skeleton or just?
Yeah, everything's happening in the cubical metric. So these are geodesics in the one skeleton. So equivalent like conjugacy classes. And I'm also going to think of these geodesics as up to homotopy. So if there's multiple geodesics of the same length, just pick one. They're all viewed to be as equivalent. And then the space for X star is X with the GI off. And then we're going to want to cubulate the fundamental group of the space. So
What's the simplest example of presentation?
Sorry?
What's the simplest example of presentation?
Take a surface with a geodesic on it. Or I guess the simplest example would be in a graph, right? Take a graph. So you want me to draw a picture? Is that what you're asking?
Oh, it's a cubical presentation of the quotient.
Yes. X star is this quotient space, right? It's the space with cube complex with cones added to some geodesics. And we want to cubulate X star R via Sadeev's construction, which Jason has helpfully reviewed this morning, although we're not going to take subgroups directly, we're just going to build walls in the space. So for those of you who are experts on cubulating things via Sadeev's construction, here's a picture of where we get the walls, right? Walls in X star come from joining together hyperplanes in X that are halfway across right, so here's your GI cell. You were implicitly asking for a picture, so here's a picture of the geodesic. GIs, and then you take, if you like, subdivide your original complex so that all geodesics are of even length, and then take each edge and pair it up with the edge that's exactly halfway across from it. The edge of this geodesic determines a hyperplane in the original cube complex, and this hyperplane is going to be part of the same wall as the hyperplane on the opposite side. So,
Secretly, are you passing through some 2-power and 4-cover and Gromov?
sorry?
Are you passing through some 2-power and 4-cover of your complex?
Oh, no, I two cover and
You have 2-power n.
2 to the power n. No, there's no secret passing of covers. I mean, some constructions live in the universal cover. There are maybe some semi-secret subdivisions of the original cube complex, but you know that's completely harmless from the point of view.
There's no double dot cover.
Sorry?
There's no double dot cover.
No, there's no double dot cover. It's none.
That's what.
Yeah, none of that.
So the secret is when GI is odd.
Yeah, then you just take the cubical subdivision of the original complex and then do the rest. Oh, So how you build a wall space and therefore an action on a cube complex with a quotient is more or less canonical, but we want this to have nice properties. And sort of the key question is, in order to have nice properties of this, let's say, the dual cube complex, X star, right, well then, how many relations are you allowed to choose, right? This is going to be a probabilistic statement. The theorem that I will eventually say will be a probabilistic theorem about random groups. So the question is like, how many relations are you allowed to take? And similarly, how are the GI, the relations? So there's going to be a probabilistic theorem about these things. And it turns out that the answer to both questions, which is how many relations you can take and how to choose them, has to do with the growth of the original group. So I sort of have to take a detour into growth in order to talk about it. Okay. So here's a theorem of growth, theorem of Futer and Nyper regarding growth of hyperbolic groups. Says that if you have a hyperbolic group, hyperbolic X is really any space, let IL be the number of closed geodesics. As before, these are equivalent to conjugacy classes. Most L. Then there exist positive constants, 1 and A2, such that for L sufficiently large, the number of closed geodesics of length of most L is bounded above and below by essentially exponentials in L and B. A1 e to the BL over L, A2 e. So if you ignore this factor of L in the denominator, this is saying that the exponential growth rate of the group is exactly this constant. And in fact, if you just wanted to count elements of the group as opposed to conjugacy classes, then you can get rid of this L in the denominator. But if you want to count conjugacy classes, then this is what you get.
non-elementary hyperbolic group.
I'm sorry?
Not versus cyclic.
Say?
The group cannot be versus cyclic.
Oh, yes, 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 non-elementary. Thank you for keeping me honest. You are absolutely right. So B. Exponential. Of G.
Hey, Dave?
Yes.
On the previous work, when you say walls and X star come from what the thought?
Yes.
Walls and X universal cover X star?
Is it okay if I don't go down the book? Since this is being recorded, I'm glad you guys are asking all the clarifying questions and ironing out all the little lies that I am unsuccessful at attempting to. All right. So maybe some examples are in order at this point. So let's say if X is is a rose with n petals. And then G is just going to be the free group of rank n. Then the growth rate, the exponential growth rate, is going to be the log of 2n minus 1, which is another way to say it, is that the base of the exponent in the exponential growth is just 2n minus 1. This you can get just by counting. A slightly more sophisticated example is if you take a hyperbolic manifold. Closed. Then the hyperbolic growth rate is just n minus 1. This is Huber in dimension 2, and this in general. So these are two kind of well-known special cases of this that were worked out for each other. Okay. And then here's a related proposition having to do with cube complexes. This is Francois Bermani himself and Dani Wise. So let G be I1x, where x is a compact, non-positively curved cube complex. G non-elementary. I'm going to preemptively add the hypothesis so I don't tell a lie. X not a product. Let H G be stabilizer of a hyperplane of universal cover. Then exponential growth rate of H is strictly smaller. Hyperplanes grow strictly smaller than, strictly slower than the ambient. I believe Dani tomorrow morning is going to talk about growth much, much more extensively than I will here, so for now I'll just mention this because I want to use this. Okay, so with that background, I can start making some sort of statements about choosing elements at random, because for people who are experts, we're going to be working in the Gromov model of random groups, where you choose more and more relations the longer they go, and how many relations you are allowed to choose definitely depends on the group. So this is part 3 of the talk, which is generic functions. Okay. So we're going to, as before, start with x, a cube complex. Those adjectives, compact and non-positively curved, are presumed. We're going to choose closed, closed. G is x, G1, up to Gk, uniformly at random from among all closed physics. Style. BL. And the key thing here is this number, k of them, where how many geodesics are you allowed to take? K is upper bounded by e to the BL, which is the growth of the whole group. But we're going to multiply by number d, which is to say take the dth root of the number of all the available relations, and d is strictly between 0 and 1. It's called density. So this is the Gromov density model of random groups. And then we're going to be making probabilistic statements about, at various densities, what sort of conclusions hold with large probability for the quotient. So quotients of G in the free group a lot is known. Okay. So in the following statements, W over OP means with overwhelming probability as the length cutoff goes to infinity. The idea here is that for any particular length bound, there's finitely many group presentations that you can make this way. Although there's a very large number, it's still finite. You just count them and you see what happens probabilistically, and then you let the length cutoff go to infinity, and then you see sort of which event lengths, the desired thing happening or the undesired. A little bit of background on what generally happens. So the next bunch of results are all for quotients of a free group as written down over there. So if your density is bigger than a half, then with overwhelming probability, G bar, which is just the quotient of G by these relations, is Gromov, right when he introduced the notion of random groups. At this point, I might already hear some experts objecting trivial or Zmod 2. I'm taking things of length at most L rather than things of length exactly L, so that actually kills the two torsions. On the other hand, if density is less than a half, then the quotient is with overwhelming probability, quotient free, hyperbolic, two-dimensional. Gromov. Yes.
I wasn't worried about the Zmod but I'm slightly worried about this thing about like having less than or equal to this sort of maximum. So most of the collections are just going to be as many as possible?
Most of the collections are going to be as many as possible, just because of the exponential growth.
Okay.
Right. Or I think, okay, I should say, for most of the theorems that I care about, density is going to be upper bounded by something rather than lower bounded by something. So I think this is about the only time when you have to be worried about taking fewer things than you're technically allowed to take.
Yeah.
Okay?
Was it okay?
I think it's okay, but in any case, I mainly care about situations where the density is upper bounded. So, let's see, if density is less than a half, then G bar contains quasi-convex surface subgroups. This is cylindrical in a three-manifold sense. Manifold groups. This is very important. So there's lots and lots of nice subgroups contained by these hyperbolic groups at small density. And the density is less than 1/6, then generically the quotient is cubulated. Density is bigger than a third, then generically G bar. T, this is Wise, and this is okay. So lots and lots of nice properties for random quotients of groups. Not so many people have studied random quotients of other groups, and that's sort of where our work is. So other groups. Here's our main theorem. Dani Wise. So let G be cubulated, hyperbolic, and in particular, I want X. X is curved complex. And I need to define a couple of quantities having to do with growth in order to formulate the theorem. So let B be a growth exponent of G acting on the universal cover of X. This is the thing. This is the thing in the coordinate sniper. A is the maximal growth exponent of a hyperplane stabilizer. The important thing for the theorem is that it's strictly less than b. That's by the proposition over there. And now we're going to choose closed geodesics G1, J of length most L probabilistically, where what's the density? Well, the number of closed geodesics you're allowed to choose has to be less than e to the VL over 41, which is to say less than density 1 over 41. And it's also less than e to the b minus a L. And then, with overwhelming probability, the quotient group, G bar, which is G with all those things as relations. Is cubulated and therefore by theorems of Agel and Dani Wise and so on has all these really nice properties where it's virtually special and pleasant. So that's the main theorem. Let me maybe pause for a moment to see if anyone has questions before I tell you a little bit about what goes into it. I know the statement is a little bit of a mouthful. We did manage to get explicit sort of density cutoffs at which this is true. Surely this is not close to sharp, but the key thing is that at sufficiently low density, nice things happen. So roughly speaking, we like to take the 41st root of all the available relations, and the 20th root relative to sort of the gap enclosed between the different segments.
So the non-cumulative version of that, that's 1 by 12, that's what they want.
Yeah, essentially 1/12. I think 1/14 is what's in the manuscript. Somewhere in there. The first time, it's funny that you say that because the first time I gave this talk, Misha Gromov was in the audience, and he started, he was very well behaved for the first 20% of his talk, and then he started asking a lot of questions. He started asking a lot.
He until he spoke.
No, he asked many friendly questions, and then he, was very concerned about, why 1/12 or why not 1/6 for the hyperbolic version. And let's just say there was a vigorous discussion. And it reminds me of this being So yes, you're very sharp. You picked up on that. But yeah, I think in the cubical setting and in the cubical version of small cancellation theory that's about to start playing a role, it seems that density 1/14 or equivalent, like C prime 1/14, is where there is a written proof of the hyperbolic. Maybe something stronger is also. Other questions?
Will we get some idea why this, so there's a, that B minus 8 part of the.
Oh, yeah, no, I'll definitely try to give you an idea of that. The one sentence answer to your question is, in the small cancellation theory that I'm about to introduce, you're worried not only about geodesic fellow traveling each other, you're also worried about geodesic fellow traveling at hyperplane. And you want to make sure that there aren't, the chance of that happening is very low, so that means that the number of geodesics you take has to be comparatively small relative to that gap. That's basically the quick answer.
Also, when you vector to this and the pre-auto result that you quoted there.
Yes.
So is there a best constant, so by which you can actually have a collection of hyperplanes cubulating, given that your group can be cubulating? You had some effective numbers saying that the hyperplane stabilizers are the best maximum hyperplane stabilizers are this much of the.
That's an excellent question. I don't know of such a result. What Dani will tell you about is that there's basically no gap between a cubulated group and stabilizers of convex subcomplexes. There the gap can be as close as you like, even for fixing the original cube complex.
Is there some sense in which, like, if you try to do this kind of generic quotient thing with property T, we'd expect this not to be true?
You would expect what not to be true.
Like, you just took some random quotient of a group,
Yeah.
with a group that had property T, you'd expect this kind of thing not to. Well,
Oh,
obviously,
random
really.
quotients of property T groups.
Yeah.
Gosh, I have no idea. I mean, you expect property T at big density and accumulated at low density, and maybe even a phase transition between the two. But
Property T is preserved under quotient.
oh, it is okay. Well, that's maybe right. All right. All excellent questions. is cubical small cancellation. So the key idea here is you study pieces, i.e. subpads of geodesics Gi and Gj, where they go. So here's my geodesic Gi. J, lifted them to the crystal cover, and they fellow travel for some large distance. I mean, you sort of, if you're trying to make this precise, have to quantify exactly, how close together does it mean to be fellow traveling. But when you have a cube complex, one way to do that is to let the cube complex make the choice for you. You take the cubical convex hull, this is convex. Let me try again. That's better. That's convex. That's the convex hull of first. This is hull Gi. Here's the convex hull of second. This is the hull of Gj, and then you take the intersection of these two convex hulls, which will also be convex, and you take a pair of points that's about as far away as possible in that convex hull, and that's the piece. Some segment connecting a pair of points at maximum distance in the intersection of the convex hulls. I mean, this is the cubical version of the theory. There's many, many variations. The key sort of course idea is that these two geodesics are fellow traveling for a long distance. And the idea of small cancellation theory is that this should happen relatively little.
So any geodesic joining those two points is a piece?
Technically, the intersection of the convex hulls is as a piece, is the technical definition in the cubical version of small cancellation theory. But if you like, here everything is happening when the original cube complex is hyperbolic. So the convex hull of Gi is lies within some bounded neighborhood of it, and the convex hull of Gj lies within some bounded neighborhood of it. So you're taking two sets that are quasi-lines and taking their intersection. It's going to be uniformly Qi to a line segment. And as certainly part of what happens in this game is that additive error is just completely irrelevant. So essentially, take it. Okay. So cubical or more general. Pieces should be small compared to the lengths of I and Gj. So this was originally developed in its earlier form by Dani, developed quite a bit further by Martin Remender. There's a great story to tell about how I found out that living in Philadelphia and teaching at Philadelphia Community College. Many other people have contributed to it, and the version I'm using in particular was developed by Dani Wise. So the precise definition is that a cubical presentation X with quotients G is C prime alpha in 0, 1 if the following things hold. So for all I and j, each piece between gi and gj is shorter than alpha times the length of gi, of course. Shorter also than gj, and for all I, each piece between gi and a hyperplane carrier. Similarly, shorter than so I think, Neil, was it you asking the question about why the condition, why the sort of second hypothesis is necessary? It's basically to rule these guys out. And similarly, the definition of a piece here is, again, the intersection between the cubical hole, the geodesic, and the hyperbolic. But that's exactly what it is.
The low one is alpha or alpha prime?
Alpha, so sorry, alpha.
Or but is it really? I mean, does it work with alpha prime less than e bar 1/20, and alpha is equal to 1/41? For the cone pieces and the wall pieces.
Yeah, I mean, yes. Yes. You're right that this hypothesis is going to guarantee the first, the cone pieces, and the second hypothesis is going to guarantee the wall pieces. So here are non probabilistic statements ensuring properties of the quotient. Where the version in Dani Wise's manuscript, I think this is going to answer your question, Mahan, is that C prime 1/14 ensures that the quotient is hyperbolic. And the thing that's probably implicit in Dani's manuscript, but we sort of had to upgrade it a little bit together, is that C prime 1/20 plus all GI primitive implies that the quotient group is cubulated, which includes the statement of this quotient group.
Do you only need primitivity to rule out the
Yes. You only need permittivity to rule out sort of the obvious. Once you rule out the obvious version of the quotient, then you rule out all.
So in particular, if you chosen to choose the normal version of cubulated.
Yes, then you would get the normal version. That's right. But it turns out that if I had chosen to use the normal version of cubulated, I couldn't loosen this 120. So the thing that ensures torsion freeness in the absence of obvious torsion, is the same thing you need otherwise. That's why, right? Of course, you don't need any sort of fancy probability or fancy counting to see that almost all your relations are going to be primitive. So you sort of get torsion freeness for free in the probabilistic statement. Absolutely. Okay, so since maybe in the 3 minutes left, let me give you sort of one particular probabilistic lemma. Is that row density pieces are rare. So here's one sample lemma. There's several more in the same flavor that suppose Gi and Gj are chosen at random from among all closed geodesics of length at most L, and then for all L sufficiently large, and for all D bigger than some constant times log L, we're going to upper bound the probability of a piece between them. Probability of piece of length at least D between Gi and Gj, that probability is at most e to the minus d times the growth of the n. So in particular, if your geodesics are of length at most L, which is what will happen generically, then you're looking for pieces of length about 1/20th of that length. So the probability of piece of length, by the way, this is Stephen's lemma, right? The probability of pieces of length at most, at least over 20th, that is minus L 20, just substituting that for D. So if we take G1 up to Gk, where K is less than e to the minus DL over 40, okay, you have this many geodesics, which means that you have the square of that number of pairs of geodesics, and you have to consider pairs in when you're looking for pieces. Then the square of that number is going to beat out that number, right? Then the wrong probability there are no pieces for any pair. And you have to do something similar with
Questions? So it was that 41 wasn't just the square root of that
I'm so glad you asked. Yes, I was hoping somebody would mention that the square root of this, this is 40, and over there there's a 41, and then I realized that the answer to that question is the thing that I was scribbling really fast, in the last negative 30 seconds of the talk, right? There are no pieces of length bigger than this absolute cutoff. But what you need for small cancellation theory is no pieces bigger than a certain fraction of the length of the geodesics itself. So you need to combine that with a statement that almost all of them are very close to the maximum length. And it turns out that's where you have to go up from 40 to 41. You have to sort of consider all the different, it's just about taking all the different independent events that could each, give you something bad and, summing those probabilities. Do you have an alternate proof?
Professor Futer, do you permit your co-author to ask a question?
Oh my God!
Okay.
I think yours the chair should permit
word next time.
That's good, that's good.
What happens when X is a surface?
What happens when X is a surface? What an excellent question. Okay. When X is thank you. What happens when X is a surface is you don't have to worry about this. And the reason the reason is that the hyperplanes in a surface group are cyclic. So I mean, okay, if it's a surface and you cubulate it using curves as your walls, which is sort of the only reasonable way to cubulate a surface, I can tell Jason being concerned, right? In any reasonable cubulation of a surface group, the hyperplanes are cyclic, therefore their exponential growth rate is 0, and and therefore this will be out of bounds. So then you just have to worry about low density, and in particular sufficiently low density quotients of a surface group are all cubulated.
Well, yeah, so I think we'll try and stick to the usual time. So we're going to make that here at 4. Yeah. Yeah, let's thank David again.